Hey, what it do? It's your boy Marty Parks again. Video number 2. This is for Network Science and Applications, EEL 6935. The title of my project was Implications of Self-similarity and Fractality in Complex Networks. So, that's what I'm going to talk about. So anyway, my main thing, this is kind of an exploration, a survey of just fractals and how they work in networks and what kinds of methods are out there to deal with, what if the idea that there could be some self-similarity or fractality in a complex network. And I mean, we hear about fractals all the time on TV. There's the movie The Butterfly Effect. We see all these really interesting patterns like the Sierpinski gasket or the Mandelbrot set. So, I was really interested in whether or not we would be able to find these same sorts of ideas, but in non-Euclidean space. Furthermore, there's a professor, UCSD, University of California, San Diego, who wrote a paper about hidden metric spaces and how self-similarity in complex networks may actually imply the existence of such a thing. And that's another piece I came across in my research that I'm going to talk about a little bit. So I'm mainly going to focus on how we can determine the fractal dimension given a complex network. And there's a couple of methods for doing that. The one I actually did myself was the box covering method and renormalization. But these are the four main ones. So we have box covering renormalization, cluster growing, and random sequential box covering method. And I'll talk about all those in more detail. So the box covering method is the primary method for determining fractal dimension for any object, like in Euclidean space. So percolation theory, that's one application that comes to mind. In order to determine the fractal dimension of whatever you really want, it could be the coast of England, that's a really common one. They'll use this idea of, box covering. So what is box covering? What does it entail? So we have to first choose a box size. And we define the box size as the number of links that each node that's in this box is away from one another. I have a nice little diagram on the next page that I found in one of the papers I was reading that I will show you when I'm talking about with that. After that, the number of boxes that we create in this manner by finding nodes that are connected in this way, that becomes our global number that we use to determine our fractal dimension. So we end up with our relationship NB proportional to LB to negative D, or in other words, we have this power law relationship where D is our fractal dimension. So it's pretty cool. And here's that photo, or this diagram I was talking about. So if we look for distance 2, we look at the picture at the top, all the way at the left, we see that we've grouped the nodes such that every node in there only is connected to no more than two other nodes. So there's only one connection. It's only connected to one other one. No more than that. Okay? See that? And now we renormalize. And that's what I'll talk about in the next one. But now, at that point, these boxes kind of get clumped together. So, see these boxes now, we see that how these are connected with one another, and we apply the same rule. So the box with the blue ones in it, that's connected to at most one, the white one, and one other one, the yellow one. So no more than the two right there. So we group all of those into a group right there. That's the new blue one. And the red one, we do the same thing. That came from the red and the yellow. And those two are grouped until we arrive at only one box at the end. You can see an analogous sort of case for distance 3 and distance 4. So the greater your distance, the faster this converges. Cluster growing is another method. I didn't try this one out because there's actually a lot of inherent bias, which may be obvious after I go through how it works. But you start with a randomly chosen node, and you create a cluster that's based on the nodes that are a minimum distance away from this first one. So you define your distance just like you did before, except now, starting from this node, you include nodes that are, L hops away from this one into a box. And after you do that, you say, all right, here's a box. You do it again with another randomly chosen node. And after all is said and done, you're going to compute the mass of each of these boxes that you've created in this manner, and you're going to average the mass across all of these boxes. And the mass is defined as the number of nodes that's in each box. So this is another way, and you get a very similar sort of relationship that we had in the other page over here, except in place of NB, look at the bottom of that equation, in place of NB we have the mass. That's proportional to the length, or the distance, raised to the negative fractal dimension. So the random sequential box covering method, this kind of combines the two. It combines box covering and cluster growing. The main difference is that there is a random process, which I'll talk about in the next slide. I'll go in more detail there. It's a random process. You choose a node and you branch off from there. And it also allows nodes that may have been included in a previous box to be included in a box in the new set. I didn't actually get to try or implement this one with my data, but it'd be interesting to look at that in the future. So here's the algorithm. We label all the vertices as not burned, just the label, and we select a vertex randomly at each step. This vertex is going to be a seed, and we'll see what that means in a second. The seed is kind of where you branch off from, where you start, all right? So we search the network from, by a distance LB. LB is your predefined distance. It could be 2, so 2 hops, 3 hops, however many nodes are this many hops away from the seed. And we burn all of the not burned vertices. So in this case, in the first iteration, everything that you reach will be burned. And now these vertices that you just burned, they're going to be put into a box. And that is how you construct your boxes. Now, what's cool about this is that you keep on going. If you find any not burned vertices, or if you don't find any, you don't find any not burned vertices, then you get rid of that box. But you can choose nodes that were already in a box. So you have this kind of more robust way of sieving out what the true dimension may be. And you repeat this until, all the burned nodes, or all of the nodes become burned and are in a box. So yeah. Now we're going to talk about the performance. So I'm going to demo my code. Let me open up MATLAB. It's already open. And I'll kind of step through my code, show you what I did here. So I used a lot of nice open source functions from kind people and the MathWorks community. Clear all my variables. And what I did was I used the data that could be found in Watson-Strogat's paper from 1998 in Nature about power grids. It was only in this odd GML file, so I found some code that helped me interpret that. And that's essentially what this block is doing here. It's nothing really that interesting, so we'll move on from there. But once all that was done, I took all of my data, it put into a nice array where nodes were connected to nodes in one column were connected to nodes in the next column. So I converted these to integers, found out all that nice stuff, and I created a weight, and yada yada. This is all the code that pretty much gave me my adjacency matrix. So when all of this was done, we got to this point. Great, we have the adjacency matrix. That's what all of this does, and you just iterate through your array. So this is a nice function from the MATLAB BGL library, and between the centrality. Why did I choose between the centrality? Because the between the centrality can be used to find the so-called skeleton of your network. And I didn't really talk about that before, but I'll talk about it now. So you have a network, right? However many nodes, and this one it's approximately 5,000. if we find the between the centrality with respect to the edges, so we find the edge set that determines that, we can kind of collapse our network into an even more sparse thing. I mean, network's already pretty sparse if it's scale-free, small world. But we collapse it even more, and we use this measure to compute our fractal dimension. So we run the box counting algorithm on this matrix rather than the original one. But you can do both, and we're going to see that it actually turns out to give you the same thing, which is really cool. So here we are, we're computing the degree vector, because I just wanted to plot the frequency distribution. So that's that right there. And here, I ran into some issues with my memory. I guess I don't have enough on this computer. But what I did was, segmented my matrix, the edge matrix that I got from the between the centrality function. And I did box count on the first 4,000 by 4,000 chunk of the matrix, and computed that using the box counting algorithm. And I'll show you the output in just a second. And then I also just computed the ratio of the logs, because that would give me the relationship that I'm interested in for my fractal dimension. So I just wanted those numbers, so that's what line 85 is right there. And I also did the same for the end of the data, because, hey, I wanted to see if only taking a small amount of data would really affect it. And it didn't. I got the same trend, which was really amazing. And essentially that's all my code. I'm not going to run it because it takes too long, but I ran it beforehand, so I have all the output already, and I will show you that. So first thing is our degree distribution. See our nodes down here in the frequency, and this looks pretty much like a power law. I mean, with the exception of this guy right here, we have that characteristic power law distribution going on. And, Watson-Strogatz told us that it had this anyway, so we confirmed it. This is the first output from the box counting algorithm. It plots the number of boxes versus the box size. So, as you can see, with a trivial box size of 1, the number of boxes is the number of nodes, approximately, in the network. So that's kind of what's happening here. And as this increases, number of boxes decreases until you get to this point. And that's that. So this was for the first set of data, like the first 4,000 by 4,000 chunk. This is the fractal dimension versus the box size. So if I choose a certain box size, I get a different dimension. Now, this might seem a little strange. You're like, but hey, shouldn't it be constant across the whole board? And yes, but I have a feeling that the way this code works is that it takes into account the renormalization process. So in this constant area, that's probably the true value for a given box size of, for a good choice of box size. And this is the renormalized area of what you'd be using. The dimension of that, of course. This is for the latter part of the data, so pretty much everything minus the first 900 row by columns, so the last part, the last chunk. And it's very strikingly similar to the first graph, and so you can see this one is too. You get the same kind of trend. You see this constant ish sort of trend at about 1.5 for the fractal dimension. So yeah, that was rather interesting. I'm going to step through just the vectors that I created. So these give me the potential fractal dimensions for a given step size through each thing. Alright, back to the PowerPoint. So the results. So I talked about some of them already, but we'll go into more detail. So we found that the distribution has the shape of a power law. Great. We observed the fractal dimension change with respect to the box size. And now, if we use a crude estimate, you remember that sort of constant area in the middle? If I took that and I divided by a renormalized part earlier with a smaller size of boxes, I can find that gamma is approximately 2.88, and that corresponds to what we'd expect for a scale-free network. We also confirmed that the original network has the same fractal dimension as the skeleton. And I may have glossed over that kind of quickly in the output, but we could run it and you would get the same exact output. It's really cool. Alright, on to hidden metric spaces. I might be coming up to my time limit, so I'll kind of gloss over this sort of quickly. So this is the idea that there's an existing space underneath your network that has a distance metric which will satisfy the triangle inequality. Alright, so what does that mean? What does that mean? That means that we can actually compute distances in our normal day-to-day life way that we're used to via Euclidean distance, more or less. That's what we're trying to do here. Alright? And why is this great? Because, well, pretty much what I just said. So now how do we do it? We look at clusters. Alright? We use clusters to get what we want. So self-similarity actually gives us the means for using these clusters that we want to use. Alright? How does this happen? The clusters will give us a probability sort of metric, which depends on the actual cluster itself, which is kind of a measure of closeness, and the desired distance that we're looking for. So this probability is dependent on these two measures. Alright? So we can look at it as a function of d over dc. D is the distance that we're measuring in the metric space, and dc is the scaling factor, which depends on the size of the cluster. And if you think about it, this coefficient corresponds, it kind of encapsulates this idea of closeness, because if you're in a cluster, you're close to your neighbors. So this distinguishes, nodes that are, quote, far and, quote, close to one another. So this gives us a nicer way of describing that idea. Now, there's a lot of mathematical detail that would be sort of trivial to go over in this video because it's kind of an overview of what I did. But the paper is by Serrano, UCSD professor. I can put the link in the description. I highly recommend looking over that because there's some really cool stuff about how to use these ideas of hidden metric spaces and how you can use these ideas of clustering and self-similarity to actually generate this metric space. So let's look at some conclusions. What did we learn from this? Well, we found that computing the fractal dimension is actually robust to some of the data loss, because when I did my computation earlier with the box counting algorithm, I got the same results even though I was missing nearly 1,000 by 1,000 data points, almost 1,000,000 data points. I still got where I needed. Skeletons, the original networks, tended to the same fractal dimension, so the trend was the same in each of those graphs. Hidden metric spaces allow for the possibility of simpler computations in networks. So, imagine, rather than having to, find the shortest path, for instance, that's a pretty difficult problem if you want to actually, go through every single possibility. Well, if we had a metric space, we'd be able to just, use our general notion of Euclidean distance and maybe take a derivative and figure out where our shortest distance is. So that's one example that will cut down on computation, if this is in fact a real thing. And it's just being postulated right now. Another example is facial recognition. This is a really popular one with image processing. You take a picture of someone's face, you have a 1,000,000 pixel image. A lot of that information is redundant. We would like to only use maybe the most important measurements of that. How can we efficiently determine which ones are the most important? And a lot of this has to do with the underlying geometry and how nodes in this image, for instance, maybe the nodes between your eyes or your mouth and your nose, how they're connected, and if there is any sort of geometry that underlies their topology. So this is a really it has the potential to be a very useful thing to look into problems like that. That's pretty much everything, so hope you enjoyed the performance, or rather the presentation, and thanks for watching. Goodbye.